I know in my intro video I had 8 different steps. I had really broken apart a lot of steps that could be collapsed into the same step, and it might make things a little bit easier. So let's simplify this hypothesis testing just a little bit. In following the book suggestion, this established process summary, step 1, we're going to determine our hypotheses. And recall that H1 or HA indicate that alternative hypothesis. Remember that the null and the alternative are contradictory. The idea here is I'm going to take each one of these steps and apply them to this problem that we're given. And I'll show you using both the traditional method and the p-value method in this problem so that you can see the differences between them. Statistics students believe the mean score on the first statistics test is 65. An instructor thinks the mean score is higher than 65, so he samples 10 statistics students, obtains the scores given. He performs a hypothesis test using a 5% level of significance. Data are assumed to be from a normal distribution. To determine our null and our alternative hypothesis, look at the context clues. We have a mean score higher than 65. I'm going to focus on the statistics instructor and not the students. This first sentence is extra, so I'm going to cross it out. I don't need that part. The statistics instructor is the one doing the test, so we're going to go with his claim. He thinks the mean score is higher than 65, so we would have mean greater than 65, and this would be his claim. Since I have greater than 65, this is my alternative hypothesis. To get my null hypothesis that goes with it, the mean and the 65 stay the same, but this time the mean equals 65. We'll change some colors to make it stand out a little bit better. So that's our first step. Our null and our alternative hypothesis, remember that they are contradictory. Step 2, we need to determine the random variable. To determine the random variable for our situation, X bar is going to be the average score on the statistics test. Determining the random variable helps us determine the distribution for the test that we're going to be using. We're doing a hypothesis test on a population mean, so the random variable we're looking at is going to be related to that, X. And specifically, we're looking at the average X bar. For step 3, determine the distribution for the test. In determining the distribution, we need to see what we have, what we are given, and what we can find based on the information. Since we're testing a mean and we have no population standard deviation given, we're going to use the t-distribution. Specifically, we're going to use the t-distribution with degrees of freedom equaling to n minus 1. Up here, I'm given 10 values. Since I have 10 data values, my degrees of freedom will be 9. Step 4, draw a graph. Calculate the test statistic. Use the test statistic to calculate the p-value if you're doing a p-value method. Some more information that we are given in the problem that we should write down. There's a 5% level of significance. That means alpha is going to be 0.05. Before I do the graph and calculating the test statistic, I do want to check my distribution for the test, make sure that I have all of the requirements to use a t-distribution. And the requirements for using a t-distribution is that we have a simple random sample, which we're going to assume we have a simple random sample in this scenario, and that our data is either from a normal distribution or we have more than 30 data values. We only have 10, but we are given that the data is from a normal distribution, so that allows us to use the t-distribution for this hypothesis test. Now I am going to need a little bit of room for this calculation, so I'm going to shrink a lot of my writing here. For the graph, the t-distribution looks like a normal. 0 is in the middle. And we need to calculate a t-score, a t-score is pretty much a z-score, just with the sample standard deviation instead of the population standard deviation. And because we're doing a sample, we have to use the standard error that we saw when we talked about the central limit theorem. Here's what I mean by that. When we're calculating the test statistic, we'll have our sample mean minus what we assume is our population mean divided by s over square root n. So value minus mean divided by standard deviation. This is the same structure that we had for our z-score, and we'll use it here for our t-distribution. Throwing some numbers in, first up we need to find x bar and s. I've actually already done it. I went to Google, I plugged in my data, I calculated the mean using average, and I calculated the standard deviation ST-DEV. And so I'm going to take those two numbers, 67 and 3.1972, and transfer them over here. And I'll use a different color, mean 67, standard deviation 3.1972. And now plugging it into this formula and calculating our t-score, x bar was 67. Our mean is coming from our null hypothesis. So this mean, we're going to take that 65 and use it here in this formula. S 3.1972 divided by square root 10, and we'll get a number. If I use my good old scientific calculator to do this, I'm going to use lots of parentheses here. I want to make sure there's a parentheses around my numerator and around my denominator. 67 minus 65 divided by parentheses 3.1972 divided by, my calculator is a little strange. I have to do the 10 first and then hit the square root button, and you can see up top in the display that that's exactly what happened. Square root 10. I hit close parentheses so that it calculates the denominator, and I hit enter so it calculates the whole thing. So 1.9781 is my test statistic. Looking at this graph, 1.9781 will be somewhere to the right. And this does make sense. Looking at my alternative hypothesis, mu is greater than 65. I have a right-tailed test just from that one statement. Now at this point is where the two methods diverge. If I'm doing the p-value method, I take this test statistic and I put it into the t-distribution and I get back a probability. I compare that probability to alpha and make a decision from that. If I'm doing the traditional method though, I don't take the test statistic, I find the critical value from alpha. When I find the critical value from alpha, I can plot it on this graph and then compare and make a conclusion. So there's still one more step for either method and then that comparison, but I've got to decide what to do. And I told you I would do both of them, so here we go. Let's start out with the traditional method, and we're going to compare the critical value to the test statistic. Test statistic is here. I already have. The critical value is coming from alpha. So I need to go over to Excel and calculate t dot inverse. And since I'm doing a right-tailed test, I need area to the left. The idea here is in the right side of the tail will be my alpha 0.05. So I need left 0.95 for my area. And then the degrees of freedom, 10 minus 1 is 9. So let's pop over here to Google. We'll put in 95 and our degrees of freedom being 9. And we get back 1.8331. Now, I already have my test statistic on the graph. My critical value was 1.8331. So if I put that on the graph and compare it to 1.9781, I notice that 1.8331, my critical value, which I'm going to write right here, critical value, test statistic. With the critical value, remember the critical value separates the area into a critical region or a rejection region and a non-critical region. The non-critical region is always the bigger part, so my critical region being to the right, I notice that the test statistic is inside the critical region. Since my test statistic is inside that rejection region, this means the outcome 67 is unlikely to happen by chance. This is enough evidence to go against our null hypothesis. That's why we call it the rejection region. We're rejecting the null. So with our test statistic inside the critical region, we would reject the null hypothesis. And this is using the traditional method. We're comparing t-values or z-values. In the p-value method, we compare probabilities. And the probabilities we're comparing are the p-value to alpha. We already know alpha is 0.05. Since we're comparing the p-value to alpha, we have to find the p-value. The p-value is the probability associated with this test statistic. Specifically, going back to our picture, we want this probability in the tail. So we want the probability for the test statistic, but in the tails. Let's use Google again and see if we can calculate some stuff. So we have the t-distribution, and I'm going to come over here and pull up the t-distribution for Google. I have t.dist, x, degrees of freedom, and tails. This is determining if it's a one-tailed test or a two-tailed test. The calculated distribution is one-tailed or two-tailed. t.dist. The value that I want is this 1.9781 that I calculated. 1.9781. Degrees of freedom is 9, and I'm looking at one tail, and I get 0.9603. Okay, that's definitely not a small probability. It's giving me the area to the left of my test statistic. I want the area to the right, so I take that number, 1 minus that value, and I get 0.0397 for my p-value. So my p-value 0.0397 and my alpha is 0.05. Now alpha is my threshold. Anything less than alpha means whatever I'm doing is unlikely to happen. So I compare alpha to the p-value. So we compare this p-value to alpha, which is 0.05, and I see that alpha is bigger than my p-value. Since my p-value is smaller than the threshold, this means that my null hypothesis is unlikely to happen by chance, so I need to reject it. Now, notice, in the traditional method, I rejected the null. In the p-value method, I rejected the null. This will always happen. It does not matter which method you use. You will end up with the same conclusion, provided that all of the calculations are correct. Since we reject the null for our statistics problem, going back to that p-value, if the null hypothesis is true, then this p-value means there's a 3.96% probability that the sample mean is 65 or higher. So that's really small and really unlikely to happen, leading us to reject the null. Our conclusion, we need to make sure we write the conclusion in terms of our problem, And notice that our claim is the alternative. We rejected the null, which means the null is no more. We could potentially just cross it out. And that leads us to have evidence to support our claim. Because our claim is the alternative, we can support our alternative hypothesis. We're not allowed to support our null. There aren't enough values associated with the null hypothesis, only one. So we can't really support the null. We can have enough evidence to fail to reject the null, but we can't really support it in this way. So our conclusion would be there is enough evidence to support the claim. Oh, and I'm sorry, I forgot. Step 4 was calculating all of that. This is my step 5, the conclusion. And the conclusion for our book is the rejecting or not the null, and then writing in terms of the original problem. So there is enough evidence to support the claim that the average score is greater than 65. And that's our full-blown hypothesis test. We are using a lot of hand calculations here. And again, the purpose of doing this by hand first is to demonstrate what we are doing. We just need to make sure that we have the correct conclusion and write it in terms of everyday language.